The next application of electromagnetic induction is a transformer. A transformer is a static device. Okay, let me write it down. Transformer. Okay. XMER. That's the simplification, simple way of writing it. Okay, so here is a transformer. XMER is a simple way of representing transformer. Now, a transformer is a static device because there are no rotating parts. There are three important missions in electrical engineering. One is transformer, motor, and generator. Motor and generator both have rotating parts, but transformer doesn't have any rotating parts, so it's a static device which transfers electrical energy from one circuit to another circuit. So a simple way of representing this is, here is a magnetic material. Okay, it's not a conducting material, it's a magnetic material. Okay, and there are two windings. One is primary winding, another one is secondary winding. Okay, so here we give the supply voltage, call that as V1, and current entering there is I1, current leaving here is I2. The load is going to be connected here, and that's the load, and sub voltage here is V2, and the source is going to be connected here. Whatever winding we're connecting to the source, we call that as primary winding, and whatever winding we're connecting to the load, we call that as secondary winding. Primary and secondary. Here V1 is the primary voltage, I1 primary current, V2 is secondary voltage, I2 is secondary current. So in this transformer, V1 primary voltage, I1 primary current, V2 secondary voltage, I2 secondary current. N1 is number of turns on the primary, N2 is number of turns on the secondary. E1 is the induced voltage across the primary winding, and E2 is induced voltage across secondary winding. Now, assuming there is no resistance across this winding, ideal case, so we're talking about ideal case. In ideal case, this E1 is same as V1 and E2 is same as V2. Now, E1 equal to minus N1 times d phi b by dt. E2 is minus N2 times d phi by b by dt. So as long as there is more rate of change of magnetic flux, okay, there is more induced EMF across those two windings. Now if I do this, E2 over E1, which is V2 over V1, you will end up with minus N2 d phi b by dt over minus N1 times d phi b by dt. These two get cancelled. I can say V2 over V1 is nothing but N2 over N1. Okay, so that's the relation between number of turns and supply voltage. Now you can see this induced EMF E2 is also based on the, it is working based on the Faraday's law, where N2 times d phi by dt. So this phi b is produced by the primary winding. So phi b is passing through this core. Okay, so it's going to be a closed path. Now it is linking to the secondary, and secondary is going to produce induced EMF. So it is working based on the Faraday's law. Okay, so now if V2 is larger than V1, we call that as step up transformer. Okay, and if V1 is greater than V1 or V2, V1 is greater than V2, then that is called step down transformer. Okay, so we have two types of transformers. One is step up transformer, another one is step down transformer. Now here is a symbol for a transformer. These two lines indicates that's an ideal transformer. So here is I1, I2, V1, and V2. Say I'm giving around 120 volts here, and this is 1:2 transformer. So this 1:2 represents N1:N2. Okay, what is V2 value in ideal case? V2 over V1 equal to N2 over N1. I know N2 is 1, N2 is 2, N1 is 1. So V2 equal to 2 times 120, that is 240 volt. So our V2 in this case is 240 volt. Now I'm going to take the same transformer. Okay, now rating of this transformer P equal to say 1000 watt. Okay, for simplification purpose I'm going to take this as V1 equal to 100 volt. And what is V2 in this case? So if I take this as 1:2 transformer, your V2 must be 200 volts. Okay, I'm taking this similar transformer. It is a step-up transformer. We are stepping up the voltage. Now, when I was a student like you, I used to think, can I use a transformer and step up the voltage and supply energy to the whole house? So my background is I'm from India, from a small village. When I was growing up, we used to have only power for only few hours, like 7-8 hours a day. Now I heard that there is at least 20 hours a day, since it's a rural area. I mean, whenever there is a power shortage, they always cut down the rural area first, and then based on the availability, they will cut down the city areas. Now, as I mentioned, when I was a kid, I used to think, okay, why can't we use this transformer and step up the voltage and supply energy to the whole village, okay, or whole 24 hours? We cannot do that here because, remember, we cannot create energy, we cannot destroy energy. Energy is nothing but power times time. Okay, power times time. So basically, if I give 1000 watt to this transformer, if it is ideal transformer, your P2 is also going to be 1000 watt, ideal case. In reality, most of the transformers are 90-95% efficient, so it will give you only 950 or 900 watt. But in ideal case, if I take 1000 watt here, it will give you 1000 watt. You cannot step up the energy. All we are doing, we're stepping up the voltage. So whenever we step up the voltage, so can I say P1 equal to V1 times I1 and P2 equal to V2 times I2. So P1 and P2 are same. So V1 I1 equal to V2 I2. So V2 over V1 equal to I1 over I2, and I know this is N2 over N1. So whenever I'm stepping up the voltage, automatically I'm stepping down the current. So based on this, you can see what is my I1. So if my P1 equal to 1000 watt and V1 equal to 100 volt, what is I1? I1 equal to 10 ampere. Now P2, power in the secondary winding, is 1000 watt, and V2, it is step up transformer. I end up with 200 volt. Okay, what is I2? Which is just 5 ampere. So whenever I'm stepping up, so here V2 is larger, so I'm stepping up the voltage. At the same time, I'm stepping down the current. So we cannot create energy, we cannot destroy energy. So whatever energy we are giving, it will give you a little less than what we are giving it to the transformer. Ideal case, we will take that's equal. P1 equal to P2. Ideal case, no losses. Now, what happens if I give a DC supply to a transformer? So here is a symbol for transformer. Now, if I connect a DC supply to a transformer, now, is there any rate of change of magnetic field here? No, because there might be a little when I just turn on the switch, but after a long time, once the switch is closed, after a long time, there is no rate of change of magnetic field. There is no rate of change of magnetic field. There is no link to the secondary. So there won't be any EMF induced here, because when we connect a DC, there is no rate of change of magnetic field. Since there is no rate of change of magnetic field, there won't be any voltage induced in the secondary. Now it's going to act like a short circuit here. It's going to act like a short circuit, and huge amount of current is going to pass through it, and it will damage the transformer. So never ever connect a DC to a transformer. Okay, so if you connect a DC to a transformer, it will blow up the transformer. Now I'm going to talk about what is the use of a transformer. Usually, we have power supply here, a generator. Okay, that's the symbol for generator, and here is a transformer, and here is a load. Here is a load center. So if you look at our WSU, Wichita State University, I think we consume around 10 megawatt of power. Okay, so this is a 11 kV transformer. Okay, for time being, let me take this as a 10 kV generator with a power rating of say 20 megawatt. Okay, so here is a 10 kilowatt generator, 10 kV 20 megawatt generator, a 10 megawatt load. Okay, so what I'm explaining here, why do we need a transformer? Say this power is coming from far away, like 10 miles from here. Assume that this has a resistance of R. Every conductor will have some resistance. We know that R equal to rho L by A. Rho is resistivity, L is length of the conductor, A is cross-sectional area of the conductor. Okay, so for sure it will have some resistance. For time being, I'm taking that resistance as 1 ohm. Okay, so here the voltage here is 10 kV. In reality it is less than 10 kV because there are losses. So out of 10 kV, what is the current taken by this load? P equal to VI cos theta. I haven't talked about cos theta in this class. Let me take that as 1. That's called power factor. Cos theta equal to 1. Don't worry about it. P equal to V times I. So V is 100K. This is 10K, and this is 10M. This is I must be 10M over 10K. That will give you 1000 ampere. So 1K, I equal to 1 amp, 1K. Now there is 1000 ampere of current passing through this wire. So there will be some power losses. Power losses are nothing but heat. P equal to I square times R. If I use that, 1000 square, so 10 cube square times R is 1 ohm, so that is 10 to the power of 6. So that's 1 megawatt. So basically, to supply 10 megawatt of power, it has to generate 11 megawatt of power. So it has to spend that extra either gas or coal or whatever it is, extra energy to generate that extra. And at the same time, we are wasting that energy in this wire. So wasting is nothing but it converts that energy into heat or light. Basically, it is going to convert into heat. So the life of this line is going to go down. Now I'm going to do the same thing with the transformer. Okay, I'm going to use 2 transformers here. That's 1 transformer. It's just very close to the generator. And here is another transformer that is very close to the load. Okay, so this distance is take 0 meters. Okay, so and this resistance is still rho L by A. I'm taking that as 1 ohm, for both conductors. Here also for both conductors. Now here I'm still using 10 kV. Here 10 megawatt and 10 kV. Okay, now here I'm using a step-up transformer, 10 kV to 100 kV, and here I'm using step-down transformer, 100 kV to 10 kV. Okay, now what is the voltage across this? Basically that's 100 kV. Now what is the power? P equal to VI cos theta. Let me take cos theta equal to 1. So VI equal to 100 mega over, or 10 mega over 100K, will end up with only 100 ampere. Okay, so the current passing through this wire is only 100 ampere. Now P equal to, or power loss in this line, I square times R. I mean, you can use I square times R. P is VI cos theta. You can use any one of these formulas. I know I know R, so I'm going to use I square times R. P equal to I square times R, so which is 100 square times 1. How much is that? That is 10 kilowatt. See, it used to be 1 megawatt. Now it is only 10 kilowatt. So it almost reduced 100 times. Okay, so that means we are saving that much fuel on the generator side, and the life of this line is going to increase. So that's the advantage of a transformer. Transformer will reduce losses in the transmission line. Thank you.